Alright guys, in this video we're going to cover the last part of graphing rational functions, which is going to cover what happens when we have a graph with holes in it, when we have what's called an oblique or a slant asymptote rather than a horizontal asymptote, and then we're going to also cover straight into it. Let's say we have the function 2x squared minus 5x plus 2 over x squared minus 4. If we're going to follow the same 6-step process that we've been following, we're going to factor the numerator denominator, we'll find the implied domain, we're going to reduce the function. That's what's going to allow us to identify the holes. Then we're going to determine any horizontal or oblique asymptotes, which we'll talk about that also. Find the intercepts, plot additional points, and then use the additional points to create the graph. Okay, so this specific example is going to go over a graph that has a hole in it. That's what this example is here. So just real quickly, guys, 2x squared minus 5x plus 2. To factor this is a trinomial that doesn't start with 1. So we're going to have to find the factors of 4 that make 5, which are 4 and 1, both negative. And when we do factor by grouping, we get x times 2x minus 1, and then negative 2 times 2x minus 1, which means that this factors to 2x minus 1 over x minus 2. And then, 2x minus 1 times x minus 2. And then the bottom of this is a difference of squares, which just factors x plus 2, x minus 2. Okay? So now that we've factored the top and bottom, we see that the implied domain is going to be, we cannot have a division by 0. So x plus 2 cannot equal 0, x minus 2 cannot equal 0. So we get x cannot equal positive or negative 2, which is the same thing we had in the last video. So negative infinity to negative 2, negative 2 to 2, 2 to infinity. Now, what we see here is the x minus 2's cancels, so this function actually reduces down to 2x minus 1 over x plus 2. So the fact that the x minus 2 factor was removed tells us that at x equals 2, the graph has a hole. And then since x plus 2 remained, x equals negative 2 is a vertical asymptote. Okay, so we've identified that there's a hole or vertical asymptote. So just like in the past videos, we're going to come over here and at negative 2 we're going to draw our vertical asymptote. So then the question goes, well, where do we put the hole? How do we know where the hole is? Well, if you remember in the last video, I said that the two functions, the function that's not reduced and the function that is reduced, are identical in their look. Besides, at the hole, the reduced function has a small hole in the graph. So what we're going to do is, for the remainder of this problem, we're going to use the reduced function. And since we know that there's a hole at 2, we're going to plug 2 into this function. And when we do that, we get 3/4. So there's going to be a hole at the ordered pair 2, 0.75. So we're going to come over here to 2, we're going to go up to where 3/4 would be, and we're going to draw our hole. Okay, so if we tried to plug 2 into the original function, 2 squared is 4, 4 minus 4 is 0, and the fact that we would be dividing by 0 would give us an undefined answer. So we would not be able to identify where that hole is. But using the reduced function, we are able to identify where that hole is. Alright, so we've identified the hole in the asymptotes, the vertical asymptotes. Now we're going to move on to our horizontal asymptote. And just like always, we compare the degrees. So if we look at the degree on top, and with this one, guys, we're going to want to go back to the original function. So the degree on top is 2, and the degree on the bottom is 2. Okay, so since the degree on the top and the degree on the bottom equals, the horizontal asymptote is at the leading coefficients divided, which in this problem the leading coefficients are 2 over 1, which is at 2. So we have a horizontal asymptote at 2. So what we're going to now do is go to our graph, and at 2 on the y-axis, we're going to add a horizontal asymptote. Okay. So then from here, we're going to find the intercepts. And once again, to find the X intercepts, we're going to set the function equal to 0. Now, we have already identified the whole, so we don't actually need to work with the original function. When we're finding the intercepts, we can just work with the reduced function. So we get 0 equals 2x minus 1 over x plus 2. We're going to times both sides by x plus 2, which gives us 0 equals 2x minus 1, which gives us an x-intercept at 1/2. Okay? And then to find the y-intercept, we're going to plug 0 into the function, and we get a y-intercept at 2 times 0 is 0, minus 1 is negative 1, 0 plus 2 is 2, so we get a y-intercept at negative 1/2. And remember, our additional points have to be beyond, in between, and above all the intercepts and the vertical asymptotes. We only have one vertical asymptote, and we've already got our intercepts. So right here, we already have enough information that we can kind of just go ahead and draw this picture out on this side. So the only additional point we need is going to be over at negative 3. We need to know, is the graph up here, or is the graph going to be down here? Okay, so our additional point is going to be at x equals negative 3. So we're going to plug negative 3, and once again, we can use the reduced function. And when we do this, 2 times negative 3 is negative 6, minus 1, negative 7. Negative 3 plus 2 is negative 1. And then divided out makes 7. So at negative 3, we're going to plot the point 7. So 1, 2, 3, 4, 5, 6, 7. It's going to be somewhere up in here. And the accuracy of that point's not as important as just realizing that tells us that over here the graph looks like this. Okay, and then just as always, guys, I'm going to jump over to show you that this does indeed check. So if I go to Desmos and I type in the function 2x squared minus 5x plus 2 divided by x squared minus 4, you see that we do end up getting a graph. Now, I went ahead and typed in the original function. I just want to show you, what if I went through and typed in the reduced function, 2x minus 1 over x plus 2. And what you'll notice is the two graphs look almost identical. The difference being, though, is that trace command. If I do the trace command over here at 2 on the original function, we see that we get 2 comma undefined. Okay, if I can get my fingers to cooperate. There we go. So the graph does indeed show a hole in the graph. The reduced function is 2 comma 0.75, which is what we found. We found that the hole was at 2 comma 3/4. But the reduced function does not have the hole, whereas the original function, which is what we were trying to graph, does indeed have the hole. So it's important to realize how to identify the hole, and then that's the process to finding the hole. Alright, guys, and then for this next example, f of x equals x squared minus 4x plus 3 over x minus 2. This is going to be an example that covers, here's what happens when we have a slant asymptote. So just run through the same process, guys. To find the domain, we see that x cannot equal 2. So the domain is going to be negative infinity to 2, 2 to infinity. Let's go ahead and factor this. The top factors to x minus 3, x minus 1 over the denominator of x minus 2, and we see that the function did not reduce. So that means that the implied domain x cannot equals 2 means at x equals 2 there is a vertical asymptote because it didn't reduce down. So we're going to come over here to 2 and put a vertical dotted line. And then now we come to the next part, which is the horizontal asymptote. In this case, it's actually what's called a slant asymptote. Alright, so if you look at the degree on top is 2, and the degree on the bottom is 1. And when the degree on top is bigger than the degree on the bottom, that means that there is no horizontal asymptote. However, when n is exactly 1 more than m, there is a slant asymptote. Okay, so notice the power on top is bigger than the power on the bottom, but it's only exactly 1 unit more. 2 is just 1 unit more than 1. Okay, that's what causes us to have a slant asymptote. So what that means is we're going to have some kind of dotted line that is an asymptote rather than a flat horizontal line. Hey buddy, hold on one second, I'm recording a video, okay? Bear with me, guys. Easton is woken up. Oh, okay, he's done talking to me. Alright, so what we're going to do is to figure out the slant asymptote is we're going to go back to long division. So we're going to divide the top, x squared minus 4x plus 3 by x minus 2. And so x squared divided by x is x. So we're going to put x on top. X times x minus 2 gives us x squared minus 2x. And then we're going to subtract to get negative 2x and bring down the plus 3. And then we're going to divide negative 2x by x to get negative 2. That's the next thing that goes on top. And then we're going to do negative 2 times x minus 2, which makes negative 2x plus 4. And then we're going to subtract to get negative 1, which is the remainder of the division problem. Okay, so the quotient, the answer to the long division problem, is the equation for the slant asymptote. So we only need to worry about this when the power on top is exactly 1 more than the power on the bottom. And if you need to go and find some videos, or refresher videos on how to do long division, that's fine. But x minus 2 is going to be where the slant asymptote is. So what that means is on our graph is we're going to come down to negative 2, because this is a linear, this is a linear function. So we're going to come down to negative 2, and the slope is up 1 over 1. And we're going to add a dotted line for our slant asymptote. Okay, so that's going to be, instead of having a horizontal asymptote, we have a slant asymptote, and that's where it's going to be located. Now, moving on with the problem. That's the hardest part of the problem, is figuring out that. Once we do that, everything's business as usual. To find the x intercepts, you set the function equal to 0. I'm going to go ahead and use the factored form. Times the x minus 2 over. And once again, guys, like I said over and over again, you just really have to set the top equal to 0. So we get x intercepts at 3 and at 1. So we have a dotted x intercept at 1, we have an x intercept at 3. And then to find the y-intercept, we're going to plug 0 in. 0 minus 3, 0 minus 1, over 0 minus 2. That's going to give us 3 over negative 2. Okay, so roughly negative 1.5. And that's going to be a dot here. And actually on this example now, we don't need to plot any additional points. We have enough information between our intercepts and our asymptotes that we can draw the picture. So the picture must look something like this. And if we jump over here to Desmos, we'd see that this does indeed check. Okay, so I've got the function already typed in. We see that there is a vertical asymptote at x equals 2, and the slant asymptote is at the line x minus 2. Okay, so that gives us everything that's in our graph. Alright guys, that can be something we discuss if we end up ever making it back into class. So, but what you have now is you have all the information you need to complete the section 5.4 homework. Okay, guys, it's important. Make sure you get that finished. Email me questions. I'd like to make like a homework video answering any questions you have on, say, the chapter 5 homework questions. And then the last video I'm going to have to cover is section 5.5, which is going to focus on sign diagrams. And I'm going to cover that topic a little bit different than how the textbook covers it. But anyways, that section will be just a one video section, and then we'll finish up with the chapter. Now once we finish up the chapter, guys, this is Monday, March 23rd. So what I want you to put on your radar is probably on Monday, March 30th, so 1 week from now, we're going to have our exam 3. Okay, and by Wednesday of this week, I will either email or create a video explaining how we're going to handle this. So there's probably my original concept is I'm thinking we're going to do like a testing window. So I'll email you the test at, say, like 2 p.m. and then you have to get it back to me by 4 p.m. So something I need you to do is once you watch this video is let me know on next Monday if there's a specific time that works best for you, or actually even better, let me know if there's a time that doesn't work for you. If you guys want to do like 9 a.m. to 11 a.m., that's fine. And I'll send this all out in an email, but I wanted to just throw this out there on the video too, that way you can kind of get to thinking about it and go ahead and be thinking about how you want to handle it once that time comes. Alright, we'll see you guys.